glean from them. So the first thing is, let's talk about a titration. We've done one before in class, but the general idea of a titration is, let's see, I need somewhere to draw. Scooch it on over. We have a flask. A terrible drawing of a flask, but we have a flask with our unknown in it, and what we don't know about that chemical is generally its molarity. So it's in the flask, and then we have a burette above it, and we are able to drip a known solution into an unknown solution. A lot of times we call the known solution the standard, or in this case, the titrant. Okay, so we are titrating the unknown with a titrant. If we actually put a probe inside of here that can measure pH, then we can track the pH of the solution as we react it. So that's what we have on this graph. We have the milliliters of titrant from the burette that have been added. So we have at 0 milliliters versus 50 milliliters of it. And all along the way, we've tracked its pH. We can see that at the beginning, with just the chemical without any titrant being added, so at 0 milliliters, the pH of our solution is pretty low. It's at 1.0. So a pH of 1.0 would tell us that we have a really strong acid right now in our flask. The other thing we can look at is where it ends up. Well, let me explain along the way. So as we add the titrant, we see that the pH steadily increases really slowly, and then we get this point where it just shoots straight up. When that happens, we have reached the point where our acid and base have equal moles to each other. So we've reached kind of that perfect place where we have that perfect mole ratio. We call that our equivalence point. Okay. Once we get past that equivalence point, the other thing we can see about it is that our pH at that point is 7 at the equivalence point. Once we get past that, all the way up to it, we had excess acid in our flask. Then we have equal moles of our acid and base, and then after it, we have extra base that has been added. So we can see that, or extra titrant, we can see that our pH at the end is really high. We have it about 12. So that's telling us that we have a strong base as our titrant, because our pH ends up really high. So there's a couple things here. We can tell where our equivalence point is. It's at pH of 7. That tells us that we have a strong acid and strong base. We can also see that we have a strong acid because the pH is really low. We can see that we have a strong base because it ends very high. This could also be switched, where we start with our base and then we're titrating it with the strong acid. We would just see kind of this whole curve flipped. So we get a lot of information from this. So up at the top it says, sorry about that, let me get this all adjusted. The shape of the pH titration curve makes it possible to identify the equivalence point, the point at which equal moles of acid and base are mixed together. So it says the following graph was produced when 25 milliliters of HBr is titrated with 0.5 molar KOH to reach the equivalence point. So we're given the volume of HBr, that's our strong acid. So that's what's in our flask, with 0.5 molar KOH, that's our strong base, and that's what's in our burette above it to reach that equivalence point. What we want to know is, what is the molarity of that strong acid? What's the molarity of our acid, our unknown acid, in the container? So the first thing we want to know is to do this calculation is the milliliters of titrant to reach the equivalence point. So how many milliliters do we actually have to add of this strong base to get to our equivalence point? So we always just find the equivalence point and then drop down to our volume. And it looks like it's at 35 milliliters. Yep, 35.0 milliliters. So if we want to then find our moles of our titrant that we used, we have its volume, we have its molarity. Rearranging our molarity equation, we know that moles are equal to molarity times our liters. So our molarity is 0.500, and our volume is, if we divide this by 1,000, 0.0350 liters. So our moles equal 0.5 times 0.035, and we get 0.0175 moles of our KOH being reacted. That's how much was added from the burette into our flask, how many moles. Now, we use our mole ratio to find the moles of our acid reacted. We could look at the reaction, HBr plus KOH forms water, because strong acid and strong base are going to form water, and KBr, simple double replacement really. We can see everything's a 1-to-1 ratio, so our moles of KOH are equal to our moles of HBr. And since one hydrogen is always just exchanged in an acid base, you can make that assumption for all your reactions, which is nice. 1-to-1 ratio. Then we need to find our molarity of our acid. So we have the moles of, remember molarity is moles over liters, so 0.175 moles. We have how many milliliters were added into the flask of our acid. So we adjust it for liters and we divide. So 0.0175 divided by 0.025, and we get 0.7. We still need those three significant figures, so 0.0 molar HBr. So there is the molarity of our strong acid. The second thing we can go ahead and do with this graph is find our acid dissociation constant, or our Ka value, from the graph. So it says at half the volume to reach the equivalence point, the pH equals the pKa. So there's a place halfway to our equivalence point where our pH and our pKa are actually equal to each other. This happens on every titration. So our equivalence point was at 35, so halfway to that is 17.5. So if we look at this, we've got 10 and 20, halfway would be 15, halfway between 15 and 20 would be 17.5. So at that volume, we can go up and find our pH. So we just have to do our best to estimate our pH. And to me, I kind of curved my line down a little bit. To me, it looks like it's at about a pH of 1.5. So the pH equals 1.5, which then equals your pKa value. Now, we just want the Ka value, so we need to undo that pKa. Anytime we want to undo something with that P, that power, we need to do 10 to the negative of that value. So 10 to the negative 1.5. 10 to the negative 1.5. And we get 3.6 or 3.2 times 10 to the negative 2. The pen's trying to die on me right now. And that would be our Ka value. Oops, equals Ka. Here we go. So this is a pretty easy way of actually finding the Ka value from a titration curve. And this will work for any of our titration curves, halfway to that equivalence point. So whatever that volume is, 35, we find half of it. And at that pH equals the pKa. And then we have to calculate from there. So those are two main things we can find from our graph here. Couple of things to keep in mind. Down below it says at the equivalence point, the pH of a strong acid and strong base is always 7. Every time. Strong acid, strong base, you're going to meet in the middle at 7. Our equivalence point, at the equivalence point, the pH of a strong acid and a weak base is blank 7. So if we still had a strong acid here, it would start low. But if we had a weak base, it would curve up much sooner on our graph. So our halfway point wouldn't be as high. It would drop it down. So it's is less than 7. And then at the equivalence point, the pH of a weak acid and strong base is blank. So if we had a weak acid, this part would scooch up, but our strong base would stay the same. So it would be above 7 or more than 7. So those are some patterns we can use to help us out in determining what kind of combination of chemicals we have. So we're going to take a look at a couple more examples using some different titration curves. So let's start with this one here at the top on your paper. So if we just looked at the titration curve, we gotta look at the pHs on it now. Here we go. If we just started with the titration curve, we can see that we're starting a little higher on our pH, but we're still ending at a very high. So we're going to be starting with a weak acid because we're starting not quite so low on our pH. So we got a weak acid, and then we're ending really high still, so we're titrating it with a strong base. So it says the following graph was produced when 10 milliliters of acetic acid is titrated with 0.350 molar sodium hydroxide. So there's our weak acid and our strong base to reach the equivalence point. What is the molarity of the acid? All right. So first thing we need to do is find our milliliters of titrant to reach the equivalence point. So we find this vertical section on our graph. And you got to do your best in estimating about where the halfway point is. It looks to me about there. That looks about halfway up that vertical section. So I'm going to follow that over, and it's right above 8. So we're looking at, let's see, 8. This would be 9. So I'm looking at about 8.4 for my pH. That's what I'm estimating. So that's our pH, and then our volume here is 40 milliliters. All right, from there we can go ahead and find our moles of titrant. So moles equal molarity times liters. Our molarity, the only one we have, 0.350 molar, times our volume, which is 40 milliliters. So we move that decimal over, make it liters. So we have 0.35 times 0.04, and we get 0.014, we still need 3 sig-figs of 0, moles of our titrant. So that is of the NaOH. So that's our base being dropped from the burette into our acid in the flask. So now our mole ratio, it's 1:1, so equal moles of our acid to our base. So we can just make that assumption. And then the last part, our molarity of our acid. So again, our moles over liters. Now, our liters come from how much was actually measured into the flask, so 10 milliliters, so 0.0100 liters. So 0.014 divided by 0.01, we get 1.40 sig-figs molar acid. So HC2H3O2, acetic acid. We have that. So again, it's this using your molarity equation twice with a mole ratio in between. It's not too bad to figure out. Now the other part is finding our pKa value, or our Ka value. So remember, it's where your pH equals your pKa at half the equivalence point. So if our equivalence point was 40, we take half that volume, 20. We follow that up to our curve. Looks like it's here. And then we follow it straight over and find the pH. Doing our best to make it straight. So I'm looking at almost 4. I'm going to say, estimate about 3.8 is my pH there. So at 3.8 pH, that equals our pKa value. So to undo that, it's 10 to the negative, goodness, let me fix that. 10 to the negative 3.8 equals our Ka. So our Ka would be 10 to the negative 3.8. And I'm going to put it in scientific notation since we're used to seeing that for Ka values. And we only get 2 sig figs, so 1.6 times 10 to the negative 4 is our Ka. All right, so that's not too bad. Another just type of analysis on a titration curve, this one with a weak acid, strong base. We're going to look at one more that's just a little different. You can see from its shape that it's not following the same shape as our other ones. So I'm going to scoot some stuff out of the way. All right, so this last one, we can see we're starting at a higher pH and going down to a low pH. So on our high side though, we're starting at about a pH of 11. So that's going to indicate that we have a weak base. So we're not starting quite at like 13 or 14 where our strong bases would be. And then we're ending around 1.5. So that's going to indicate we're with a strong acid. Okay, so what's in the flask first is what we start with. So we're starting with the flask as a weak base and we're ending with a strong acid. So that means that's what's in our burette. So this is in our flask and this is our burette. And that follows the same for all of them. So in the one above, we'd start with our acid in the flask and end with our base in the burette. All right, so it says the following graph was produced when 40 milliliters of NH3 or ammonia is titrated with 0.2 molar HCl. So there's our strong acid. So that means the ammonia is our weak base. To reach the equivalence point, what is the molarity of the base? So first thing we want to do is look at that volume at the equivalence point. So we can see our equivalence point, if we were to kind of estimate up halfway up this curve, I'd say it's about here. So that's going to give us a volume of 10 milliliters. And I'm going to go ahead and say that our pH is about 5.5 at the equivalence point. All right. So if we're starting with 10 milliliters as our equivalence point, we want to find moles. So our molarity of our HCl times its volume equals 0.2 times 0.01 gives us 0.002. Yep. But we need those 3 sig figs. So that's our moles of our acid. Now, a couple things, because I'm going really fast. Remember that this is your volume at the equivalence point. That's your volume added, and so that's your acid. It helps you to label this stuff. Your acid or your HCl is the one being added, okay? And then, so that's why we end over here with our strong acid, because that's the one being added. We end up with more of the strong acid. So to keep track, you're adding 10 milliliters of that titrant or of that acid. So we're using the molarity of that acid to find our moles. Just going a little faster. All right, use mole ratio to find moles of base. It's a 1-to-1 ratio. They all are. So we have that many moles, same number of moles of our base, NH3. And then we want to find our molarity of our base. So our moles of our base over our volume of our base. So there are 40 milliliters of that added to the flask. So 40 milliliters would be 0.0400 liters. Okay, so 0.002 divided by 0.04. And we have a molarity of 0.0500 molar NH3. All right, and we're going to go ahead and find our pH so we can find our pKa. So if our volume was 10 milliliters to reach our equivalence point, then half of that would be 5. So that's here on our graph. So I follow that up to our line, follow that over to our pH, we'll rise over run here, And it looks like it's about halfway between 9 and 10. So about 9.5 would be our pH at that halfway point. So 9.5 would equal our pKa. So our Ka would equal 10 to the negative 9.5. So and calculate that out. 10 to the negative 9.5 will give us 3.2 times 10 to the negative 10. And there's our K value. And I actually labeled these wrong, I feel. So this should actually be your KB value for all of these. And the reason is because we are dealing with that base. So at this first part, we have more base than acid. So that's actually our KB. So I'm sorry on that. I'll fix that. So there's 3 different examples of how we would actually go through this process. Again, it's nothing we haven't done before in terms of the calculations. We've done molarity, we've undone pH and pOH and all of those things. It's the same process for pKb. It's just how do we get the information from our graph and our introduction there. So you guys have some examples to work through, some practice, and if you need reference, you can always come back to the video or ask us in class. Also take a look at your textbook or any of the other videos that we recommended on your resource card.